Modern algorithmic trading desks demand complex machine learning strategies, but they also require strict sub-millisecond execution. These two operational requirements are completely opposed. Look at a traditional monolithic architecture. The decision engine generating trades and the validation engine checking compliance are locked inside the same processing block. When heavy machine learning inference and strict compliance checks run sequentially, it blocks the main I/O thread. The data stalls. That latency creates a backlog. Trades hit the market late. Invalid orders slip through. Back-office teams then spend hours manually reversing erroneous transactions. The solution splits the monolith. We completely decouple the logic, separating the strategy prediction from the compliance execution. We built the prediction side using AWS SageMaker and handle the real-time execution side using Java and AWS Kinesis. This asynchronous segregation allows a trading desk to scale up its algorithmic intelligence without violating strict regulatory compliance. Algorithmic strategy starts with massive amounts of historical market data. We store this raw information in an Amazon S3 bucket. This dataset consists of OHLC data, open, high, low, and close prices, combined with trading volume information over specific time periods. Researchers query this storage via SageMaker notebooks to test market patterns. We feed technical indicators, like simple moving average and rate of change, into a neural network. It outputs a binary probability predicting if a trade hits its profit target. 0 means no, 1 means yes. We take that trained predictive logic and wrap it into a deployable Docker container. Inside that container, we use an open-source Python framework called Backtrader to manage the strategy code and order logic. Containerizing the model guarantees that the exact same mathematical logic used to backtest against historical data is the exact logic running in live market inference. The SageMaker model produces highly accurate predictive signals, but that output is raw. It is unsafe to send directly to an exchange without real-time validation. When the Docker container generates a trade signal, it formats the data into a discrete, standardized JSON event packet. Routing that JSON packet directly to the trading desk execution API creates a fragile point-to-point connection. Any surge in market volume would overwhelm the API and drop trades. We introduce AWS Kinesis data streams as an asynchronous event bus, acting as a shock absorber between the machine learning model and execution engine. Kinesis organizes data using sharding, splitting the stream into parallel horizontal lanes based on partition keys like trader ID. Sharding enables horizontal scalability. The system can process massive bursts of market activity by distributing the load across multiple lanes without creating a single bottleneck. Kinesis also enforces ordered delivery. It ensures that multiple trades assigned to the same shard remain in the exact sequential order they were generated. Kinesis transforms that fragile direct connection into a durable, replayable buffer. It strictly enforces the architectural separation required for high-frequency trading. On the far side of the Kinesis stream sits the Java validation microservice. It pulls the JSON event packets for evaluation. This microservice acts as the execution gatekeeper. It has a strict engineering constraint, a latency budget of less than 50 milliseconds to validate every trade. To meet that constraint, the microservice is built on a Spring Boot framework utilizing a Netty non-blocking web server. The core design relies on asynchronous programming. When the JSON packet enters the microservice, it passes through a 4-tier rule framework, splitting into 4 parallel processing paths. Tier 1 is syntactic validation. This layer confirms basic data types and formatting are correct, checking numerical fields contain numbers and text fields contain text. To maximize speed, the system uses the Jackson parsing library instead of Gaussian, significantly reducing the time required to deserialize nested JSON structures. Tier 2 is semantic validation. This evaluates the actual values, ensuring the trade quantities and price fields fall within pre-configured business limits. Tier 3 is cross-field validation, ensuring logical consistency across the packet. Tier 4 is external validation, making asynchronous calls to Amazon DynamoDB to verify live market data. Complete Future allows all 4 tiers to execute simultaneously. The results merge into a single pass or fail status, preventing the latency of individual checks from compounding. To eliminate runtime interpretation delays, the system pre-compiles and caches all of these validation rules in memory during startup. By combining reactive, non-blocking Java APIs with parallel rule execution, the gatekeeper rigorously enforces compliance without stalling the algorithmic execution engine. This dashboard shows the results of system load testing under simulated high-frequency trading bursts. The primary metric is response time. The median latency for full, 4-tier validation sits safely under the 50 millisecond budget. Even during simulated market surges and extreme traffic spikes, the 99th percentile latency remains below 100 milliseconds. The system sustains a throughput of 5,000 events per second per service instance. Adding more microservices scales that capacity linearly. Accuracy remains strict. During testing, the validation logic caught all intentionally malformed inputs with 0% false positives. Valid trades were never incorrectly rejected. Deployed to real-world energy and metals desks, this validation architecture reduced manual trade corrections by 40%. Back-office rework dropped drastically. Modern algorithmic trading requires a decoupled pipeline. Heavy AWS SageMaker models map out the complex strategies, while Kinesis-backed Java microservices ruthlessly validate them in real time.